We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will conclude our study of waves. We will begin by demonstrating that any function whose argument is proportional to x minus vt is a solution to the wave equation with wave velocity equal to v. We will then clarify that the equation that defines mechanical waves must be derived from Newton's second law and that the wave velocity will be identified from the constants that specify the forces and masses in the problem. We will then apply the principle of superposition to demonstrate the existence of standing wave solutions to the wave equation that are generated by two waves of equal amplitude and frequency that move with opposite velocities on the same string. Finally, we will show how such standing waves are generated when an incident wave is reflected from a fixed endpoint. Last time we began our study of waves, we saw that as a wave propagates through a medium, the elements of the medium oscillate about their equilibrium position while the wave can propagate indefinitely. We studied the example of a wave on a string and we derived the wave equation, a differential equation whose solution describes the displacements of the medium as a function of both position and time. We demonstrated that one such solution was the harmonic wave, with the speed of the wave being given by the ratio of the angular frequency to the wave number. We will now show that waves of any shape, not just harmonic waves, will satisfy this equation as long as the speed of the wave is constant. We start by rewriting the argument of the cosine in our harmonic solution in terms of the velocity of the wave. We see that the argument of the cosine is now proportional to the quantity x minus vt. We will now show that any function whose argument is proportional to x minus vt is a solution to the wave equation. We use the chain rule to differentiate our function with respect to both x and t. Each time we differentiate with respect to t, we bring out a factor of minus v. Consequently, we see that the second derivative of our function with respect to t is equal to v squared times the second derivative of our function with respect to x. Note that our function, f of x minus vt, does not have to be harmonic at all. It can represent a wave of any shape moving with speed v. For example, here we see a shape described by the function y is equal to f of x. We now move the shape to the right a distance d along the x-axis. The new shape is described by exactly the same function if we just change the argument from x to x minus d, since the new argument will have the same value when x is equal to d as the old one did when x was equal to 0. Now, if this shape, we'll call it a pulse, moves to the right with constant speed v, we can describe the motion completely by simply replacing d by v times t in the argument of the function. On the last slide, we showed that any function whose argument is equal to x minus vt is a solution of the wave equation for a wave having speed v. Note that the speed v is defined in the wave equation. For a wave on a string, we used Newton's second law to obtain a wave equation described by a speed which is equal to the square root of the tension divided by the mass density of the string. The important point we want to make here is that the speed of the wave is determined by the medium and does not depend on how the wave was initially excited. For example, here we see the wave generated by our initial harmonic excitation. We'll now excite a different waveform, namely a single pulse in the string. Note that the speeds of these two different waves are the same, as they must be, since the speed is totally determined by the medium. Now, we can also excite a wave in the string by driving the opposite end of the string. In this case, the wave travels to the left and is represented by the same function, except that we just have to change the sign of the velocity. On the last slide, we showed that any function of the form f of x plus or minus vt is a solution to the wave equation where v, the speed of the wave, is determined by the properties of the medium. Now, if two different functions are separately solutions to the wave equation, then their sum is also a solution. At first, this observation may not seem to be significant, but in fact, it has profound implications for certain properties of waves. Namely, if many waves can travel in the same medium at the same time, each wave will move independently of the others, resulting in a total displacement of the medium at any time and place that is simply equal to the sum of the individual displacements. Here we see an important example of this result. We have two harmonic waves having the same amplitude and wavelength moving along a string in opposite directions. As they meet, the total displacement at that position and time is just given by the sum of the individual displacements. Now, there are two important things to notice here. First, as the waves pass each other, the sum seems to be standing still. Second, after the waves pass each other, they both look exactly the same as they did before they met. Both of these observations are interesting. The fact that waves look the same before and after they pass through each other means that the waves do not interact. One wave does not in any way change the nature of the other. This simple result has important consequences. For example, this non-interaction of the waves allows many phone calls to be carried by a single optical fiber at the same time, and ensures that the light from a distant star can reach a telescope on Earth. The fact that the sum of the two waves appears to be standing still is also extremely important. This phenomenon, called standing waves, allows us to build both microwave ovens and guitars, for example. We will investigate the properties of standing waves in more detail on the next slide. On the last slide, we saw that when two waves having the same amplitude and wavelength but traveling in opposite directions meet, the result is a wave which stands still. If we view the animation again, we can pick out some important aspects of this standing wave. First of all, we see that the amplitude of the standing wave goes from a minimum of 0 when the displacements of the incoming waves cancel to a maximum when the incoming waves lay directly on top of each other, and that this amplitude keeps oscillating as the incoming waves move past each other. Second, we see that the wavelength of the standing wave is the same as that of the incoming waves. Third, we see that there are points along the string whose displacement is always 0. All of these observations can be explained by remembering some trigonometry. We will start by writing the equations for the two incoming waves. Since the waves have the same amplitude and wavelength and differ only in the direction of travel, we see that these functions differ only in the sign of the term in the argument that involves the time. Therefore, the total disturbance is represented as a sum of two cosine functions. Now, you may recall that there is a trigonometric identity that relates the sum of two cosines to the product of two cosines. We will now use this identity to rewrite the equation of the wave as a product of two cosines, one a function of space and one a function of time. This mathematical expression describes exactly what we are seeing. We have a stationary wave with an amplitude equal to the sum of the amplitudes of the incoming waves. This pattern is then multiplied by a factor that oscillates in time between -1 and +1. On the next slide, we will discuss how to create such a standing wave. Here we see a wave being excited at one end of a string. The wave then travels down the string until it reaches the opposite end, which is fixed in place. What will happen when the wave reaches the fixed end of the string? Well, it will be reflected back with the same amplitude and frequency. We now have two waves in the string moving in opposite directions with equal amplitudes and frequencies. These waves will then produce a standing wave pattern. How can we understand the creation of this reflected wave? Recall that last time we made the case that energy is transmitted by a traveling wave. What happens when that energy reaches the fixed end of the string? Since the end cannot move, it cannot absorb any energy. Consequently, the energy must remain in the string in the form of a reflected wave, much in the same way that a ball bounces off a fixed wall. We can take this idea one step further and fix the initial end of the string as well. You will probably recognize this construction as that of any stringed musical instrument. In this case, the fixed two ends of the string define the boundary conditions for all waves that can travel on the string. Since the displacement of the string has to be zero at each end, and we know the separation between successive nodes of the wave is equal to half a wavelength, we can see that the distance between the fixed ends of the string must be an integral number of half wavelengths. The tricky thing here is how to get the wave started, since we are no longer hanging on to one end. Different musical instruments deal with this in different ways. In a guitar, you pluck the string with your finger. In a piano, the string is struck with a small hammer. In a violin, the string is rubbed with a bow. Depending on how the string is manipulated, the standing wave that results will be a combination of many of the wavelengths that are possible. Usually, the biggest contribution comes from the longest possible wavelength that the string can support. In this fundamental mode, the wavelength is twice the length of the string. Since the wavelength is fixed by the length of the string, and the speed of the wave is fixed by the properties of the string, such as its weight and its tension, the frequency of vibration of the string is also fixed. The different notes that can be played on the same string of a guitar or a violin are made by pushing the string back against the neck of the instrument, effectively changing the distance between the fixed ends of the string. Changing this distance then changes the wavelength of the fundamental, which in turn changes the frequency that you hear. The high E string on a typical guitar is usually made from 10-gauge wire, which has a mass per unit length of about 1/3 of a gram per meter. Suppose the distance between the bridge and the nut of your guitar, in other words, the length of the string between the fixed endpoints, is 61 centimeters. We'd like to determine the tension in this string when the frequency of oscillation is 329.6 hertz. How do we go about making this calculation? We will start by using the wavelength and frequency of the fundamental mode to determine the speed of the wave in the string. We can then use the mass of the string to calculate the value of the tension, which gives the required speed. We start by finding the wavelength of the fundamental mode, which is just twice the length of the string. Now the speed of the wave is always equal to the product of the wavelength and the frequency. We know the speed of the wave is equal to the square root of the tension divided by the mass density of the string. We can now solve this equation to obtain the required tension to be equal to 53 newtons. The frequencies of the 6 strings of a guitar vary from high to low as you move across the neck from bottom to top. To make the guitar easier to play and to keep the neck of the guitar from twisting, the tension in all 6 of these strings has to be about the same. Since all of the strings are the same length, the only way we can make the other strings vibrate with different frequencies is to have the speed of the waves on these strings be different. The strings that vibrate with a higher frequency must have a correspondingly higher speed. Since the tension in the strings are about the same, the mass per unit length of the lower frequency strings must be bigger. This observation explains why the strings on a guitar get thicker and heavier as you move across the neck from higher to lower frequencies. We conclude with a brief discussion of the main points of this prelecture. First, we demonstrated that any function whose argument is proportional to x minus vt is a solution to the wave equation with wave velocity equal to v. The harmonic solutions we dealt with last time should be seen as only special cases of the more general solution. We obtained the velocity for mechanical waves by applying Newton's second law to produce the appropriate equation of motion. The velocity of the wave will be determined totally by the properties of the medium, the forces that act on the masses that constitute the medium. Second, if more than one wave is excited in a medium, the resulting motion is given by the superposition of the displacements of the individual waves at each point at each time. If two waves of equal amplitude and velocity travel in the same medium but with opposite velocities, the resultant motion will be a standing wave of the same frequency but whose amplitude will be the sum of the amplitudes of the individual waves. Third, we claimed that an initial wave propagating on a string that has both ends fixed will be reflected from the downstream fixed end, producing an additional wave with the same frequency and amplitude, and will therefore produce a standing wave in the string.